Hey, welcome back. You ever stop and wonder what's actually happening when you cook an egg or, when an old iron gate starts to rust? The world all around us is constantly changing, and today we're going to learn the secret language that describes all those transformations. And that is, of course, the language of chemistry. Let's kick things off with a really cool example.
So check this out. What you're seeing is a simple ribbon of magnesium metal. But when you light it, whoa, it just erupts in this brilliant, blindingly white light. And what's left behind? Just a pile of white powder. I mean, it's a total transformation. But what is actually going on there?
And that really gets to the heart of what we're talking about today. Why do things change? From milk going sour in the summer to our own bodies digesting food, change is just everywhere. Chemistry gives us the tools to understand these amazing stories of transformation, which we call chemical reactions.
Okay, so first things first, we need to learn how to spot when one of these chemical stories is even happening. How do you know a reaction has actually occurred? Well, it turns out chemists look for a few telltale signs.
And what's really cool is just how simple these clues are. Did something change its state, like from a liquid to a solid? Did the color change, like an iron nail turning that reddish-brown rusty color? Are there bubbles? Is a gas being released? Or did it suddenly get hot or cold? These are the big clues that tell you a chemical reaction is going to.
All right, so once we've spotted a reaction, we need a way to describe it. But writing out a shiny magnesium ribbon was burned in the air and it turned into a white powder called magnesium oxide, yeah, that's a mouthful. Chemists needed a better way, like a secret code.
And the two most important words in this new language are reactants and products. It's super simple. Reactants are your starting ingredients, the stuff that's going to change. In our example, that was the magnesium and the oxygen. And the products? That's the new stuff you end up with. In this case, that white powder, magnesium oxide. See? Easy enough.
And this is where it gets really powerful. We can take that long sentence and shrink it down to a simple word equation. But then, by using symbols for each element, we get this, the chemical equation. It's like a universal shorthand that tells the whole story in just a few letters. This is the language of chemistry.
But, every language has rules, right? It's got grammar. And chemistry is no different. The single most important rule is that you can't just make things appear or disappear out of thin air. You've got to account for everything you started with. And this is where balancing comes in.
Let's look at our equation again. Mg plus O2 goes to MgO. Okay, let's do a quick head count. On the left side, the reactant side, we've got one magnesium atom and two oxygen atoms. But look at the right side, the product side. One magnesium, and wait, only one oxygen? Hold on, where did that other oxygen atom go? It's just vanished. And that's a big no-no.
And the reason it's not allowed is because of this huge, fundamental rule of the universe, the law of conservation of mass. This basically says matter can't be created or destroyed, just rearranged. So every single atom you start with has to be there at the end. We have to fix our equation so it obeys the law.
So how do we fix it? Well, we can't change the chemicals themselves, but we can change how many of each molecule we use. By putting a 2 in front of the Mg on the left and a 2 in front of the MgO on the right. Let's check again. Now we have 2 magnesiums and 2 oxygens on both sides. Perfect. The equation is balanced. Our chemical story now follows the rules.
Okay, so now we know the alphabet, the words, and the grammar. So we can start to recognize the common types of stories, or plots if you will, that these reactions tend to follow. Let's check out some of the biggest ones.
First up, we have the combination reaction. This one is exactly what it sounds like. 2 or more things come together to form one single, more complex thing. A plus B makes AB. A perfect example is burning coal. The carbon in the coal combines with oxygen from the air to make one product, carbon dioxide.
And next, we have the complete opposite, the decomposition reaction. Here, you start with one complex thing, and it breaks down into 2 or more simpler parts. So AB breaks apart into A times B. It's literally the reverse of a combination.
Yeah, looking at them side by side really makes it click, doesn't it? Combination reactions build stuff up, and decomposition reactions break stuff down. They're just two sides of the same chemical coin.
Now for a little drama. This is called the displacement reaction. So we've put a plain iron nail into this blue copper sulfate solution. And what happens?
Well, because iron is more reactive than copper, it basically just kicks the copper out of the solution and takes its place. And you can literally see it happen. The nail gets coated in that reddish-brown copper, and the solution starts to lose its blue color. One element has displaced the other.
So if one element can swap, hey, why not two? In a double displacement reaction, two compounds meet and they essentially swap partners. Their ions trade places and you end up with two totally new compounds. A lot of times, this swap actually creates a solid that falls right out of the solution. We call that a precipitate.
Right, so this isn't all just abstract stuff for a chemistry lab. These chemical stories are happening all around us, every single day, in ways that totally affect our lives. Let's look at one you see all the time. Here, we're just heating up some of that reddish-brown copper powder, and as it reacts with the oxygen in the air, you can see its surface turn black. That black stuff is a new chemical, copper oxide, and anytime a substance gains oxygen in a reaction, we call that oxidation.
And this is why that matters so much. That exact same process, oxidation, is what causes corrosion. That ugly red rust on a car, the tarnish that dulls your silverware, that green coating on an old copper roof, it is all the exact same type of chemical story. A metal reacting with the world around it and oxidizing. And get this, even your potato chips are involved. Ever wonder why a bag of chips feels so puffy and full of air? Well, it's actually not air, it's nitrogen gas. Chip makers pump out all the oxygen and replace it with nitrogen, specifically to stop the fats and oils in the chips from oxidizing. Because that oxidation is exactly what makes food go stale and taste rancid. So yeah, chemistry is literally keeping your snacks fresh.
So, from balancing equations to keeping our chips from going bad, we've seen that chemistry is really a language for understanding the constant change happening all around us. The big takeaway here is that this language isn't just for chemists in a lab, it's for all of us. Which brings me to my final question for you. Now that you know the basics of the language, what chemical stories are you going to start seeing in your world?